Hi, this is just a quick review of what we've been covering in Chapter 10. The first section that we did was we were covering exponential functions, and we wanted to know, could we write equations from a table of values like the one given. And so when we talked about exponential equations, we talked about how you wanted to recognize that all of these values were being multiplied by 2 to get to the next y value. And so we talked about when you write an exponential equation, whenever you see something as being multiplied, in this case we have y, so y equals, and the first number we have is 6, and then we multiply that by 2, and we're going to continue to multiply that by 2 on n number of times. So that's how I would take this table of values and write an equation. The other thing we talked about in section 10.1 was we talked about how when you looked at what you multiplied by, this 2, we knew this was going to be exponential growth because that value was greater than 1. So we talked about how if you had exponential growth, the b value was greater than 1. The reason we say b value is because the generic form or the generic equation for all exponential functions is y equals a times b to the x. So if this number that's raised to the exponent is greater than 1, we have exponential growth. So let's just look at another example. Again, when we look at this one, we again notice that it is being multiplied by 2 each time to increase these y values. So our equation would look like, again, y equals, the first value in our table is 5. It's being multiplied by 2. But in this table, there's one difference between our x values. Up here, we started with a 0, and in this table, we started with the value of 1. When you start with the value of 1, that means your exponent is going to be x, or n minus 1. I used n up here, and again, because we had x in our table, it should really be 2 to the x. Just like down here, I should have 5 times 2x minus 1. Again, whatever variable this is, that's the variable of my exponent. Now, we briefly talked about this in class, but we needed to kind of review our exponent rules because this is technically not written in function format. So when we have y equals 5 times 2 to the x minus 1, really what that means is we have 5 times 2 to the x times 2 to the negative 1. Remember, our exponent rules means we could have combined those together. Now I'm using the exponent rule sort of in the backwards order. What that allows me to do is I can rearrange the order of which I'm multiplying, so 5 times 2 to the negative 1 times 2 to the x. And use my exponent rules. This would be 5 times 1/2, and this would become 5/2 times 2 to the x. This would be what we refer to as function form. In section 10.2, we talked about growth versus decay. Again, the growth part is when you look at the value that has raised to the exponent, we refer to that as b, and if b is greater than 1, that's how we know that this is growth. If we look at the b value, and the b value is less than 1 and greater than 0, we say that that is decay. So in section 10.2, we just first identified the difference between the two. Then what we did is we took some equations, and some of them that we saw look like y equals maybe 4 to the x, and we started just to graph those equations, and we usually started with our sort of our general reference points. And again, that was negative 1, 0, and 1. And with our general reference points, again, we had 4 to the negative 1, which we learned was our reciprocal function. If you have 4 to the 0, we know anything to the 0 power is 1. And if you have 4 to the first power, we know that anything to the first power is itself. Again, we could continue the table farther. 4 squared, we would learn, is 16. If you wanted to do 4 cubed, we would learn that was 64, and so we created this table of values, and then we just created our graph. And what we saw was for all growth equations, again this is a growth because the b value is greater than 1, for all growth equations and decay equations, all of them go through the point 0, 1, and they continue to grow. So at the point 1, I was up 1, 2, 3, I was up at 4. At the point -1, I was down at a 4th. And so we saw all exponential growth equations looking like this in 10.2. We also then started to talk about the domain and the range of these functions. We said that the domain again, the domain is all the x values, and we said that the x values, because the graph continues to go to the left and the graph will continue to go to the right, we said our domain is from -infinity to infinity, or we again abbreviate that as all real numbers. We said the range was the y values, and what we noticed about our y values is that the graph was only positive or above the x-axis, and our answers are also positive. So we said that the y values were greater than 0. And that brought up our third characteristic, which was asymptotes. And we had one asymptote, a horizontal asymptote, that actually went right through y equals 0. And so exponential growth equations had these characteristics. Again, we talked about how every graph, whether it's growth or decay, has the intercept of 0, 1. And then we just continued to talk about their graphs. So that's what we did in section 10.2. The last section that we covered was section 10.3, and 10.3 was our transformations. And our transformations were just shifts, and so I'm going to refer to again that same function we just saw on the last slide. The values of that function, again, were 1/4, 1, and 4. And then our transformations, again, is if we started to change it. So if I said, okay, let's make this y equals 4x plus 2. Well, that would make us shift up 2. And all that did to our table was take our y values and change our y values by 2. Up 2, up 2, up 2. And it would shift our entire graph up 2. So before we have the point, a horizontal asymptote there, yeah, this is 1, 2. We will now have a horizontal asymptote there. We have the point at 0, 3, at 1 and 2/4, and at 1 at 6. And so that's how our graph shifted up to. The domain did not change. The range just shifted up 2, so it's greater than 2, and so did our asymptote. We did other functions that shifted things around. We said if we had y equals 4x and then we had x minus 3, we said that would shift us right 3. And all that would do is take our original graph and shift us right 3. So again, you go here, the table, all that would change would be this would be right 3, right 3, right 3. The y values would not change. That means the domain doesn't change. It's still -infinity to infinity. The range doesn't change, so it's still y greater than 0. And the asymptote doesn't change. Still y equals 0. So when you shift to right, it doesn't change any of those characteristics that we learned in 10.2. Excuse me. If you put the negative sign in front, we said that that is a reflection. And if you multiply by a value, so again, kind of showing what we showed in 10.1, if I would do 2 times 4 to the x, that would be the dilation. Again, reflections and dilations, again, only change the y values. So these would still be -1, 0, and 1. This would just become -1/4, 0, and -4. And these values would just, again, x values do not change with dilations, only the y values do. And you're just multiplying by 2. So 1/4 of 2 is 1/2. A fourth of, or 1 times 2 is 2, and 4 times 2 is 8. So it just stretches it out a vertical stretch. Those are the things that we've covered in terms of characteristics of graphs. The only other thing that we talked about in this chapter was continuous growth. And we looked mostly at continuous growth when we were looking at population growth. And we saw this equation given to us. And we learned that E was just a number. And so if you kind of look back, they gave us some examples of, like, if the population of Miami started as 216,500 people, and people can grow continuously, and that's why we use that E. But they're growing continuously at a 3% rate, so the R becomes 3%, and we want to know how many people will they have in 20 years from now. So T was time, R was rate, and N sub O was our starting amount. And this would just be our new amount. And so we just talked about this, and we talked about how you could plug that into your calculator. I'm going to try it down here. So turn my calculator on, clear that out. And so I'm just typing in 216,500. The E button is above the division sign, and then raised to the 0.03 times 20. So we see that in 20 years from now, the population of Miami is 394,489-ish people. So that would be how we would calculate population. Another thing we talked about when we were using our calculator, we talked about how you could graph it. So we could do that 216,500 E raised to the 0.03 times 20. And then we talked about how if you did second graph, it gives you a list of values. And you can try to type that in correctly. Oh, my bad. I shouldn't type in 20. I want to type in X because I want it to represent any year. So I want that exponent to be X. Now if I do second graph, it gives me a list of values. So I saw in the starting year, there were 216,500 people. The year after that, the year after that, the year after that. And I can keep seeing how it grows. So if I asked, well, when is it going to be 400,000 people, I just keep arrowing down, and I found out, and actually at the end of the 21st, or between the 21st and 22nd year, I get up there. So this is probably the most applicable part of the whole first 3 sections, and we're going to start reviewing this and take a little quiz starting next week. So if you have any questions about any of these pieces, please let me know. Thanks.